Hello and welcome to lecture 21 of the course Theory of Computation. In lecture 20 we saw push-down automata, push-down automata or PDAs, where a new machine model that combines the powers of NFA and an additional stack, right? So it is like NFA with an additional stack. A stack is an unbounded memory but with restricted access. You can only access the top entry on the stack, right? And we saw that it can recognize languages such as 0 power n, 1 power n, right? We saw examples, we saw the rules, right? We saw that it can recognize languages 0 power n, 1 power n, and also other languages which were not regular, meaning in NFA can only recognize regular languages, but PDAs we saw that it could do more things, right? We said that eventually we will show that PDAs are going to be equivalent in power to the context free languages, but that is not going to be shown in this lecture, but we will see it in the upcoming lectures, right? So what I wanted to just quickly mention in this lecture, it's going to be a brief lecture, is some modifications that we could do in case of PDAs, right? So number one is that right. So if you recall, we had said that if you have an NFA and it has multiple accepting states, we could convert it into an NFA that has only single accepting state, right? We can pretty much do the same thing in a PDA. So what if, so these are the old accepting states, right? These are the old accepting states, and as you can see there are multiple accepting states. So the ones in blue are old accepting states. So we can have epsilon transitions. We create a new state, the red one, this one, right? Right, we create a new state, and this one, and we make epsilon transitions from the old accepting states to the new accepting state, right? And what this will and then you remove the old accepting states are there, but they are no longer accepting states. So this becomes the only new accepting state. Okay, so this becomes the only new accepting state. So the other ones, the blue ones, are made into normal non-accepting states. So whatever string leads to any of the blue states can take an epsilon transition and go to the new accepting state, right? Hence the new PDA with this modification has only one accepting state. So this is fact number one. So given any PDA, we can convert it into a PDA which has a single accepting state, right? Number two is that we saw two PDAs, right, in the previous lecture. In both the cases, the PDA upon acceptance, the stack became empty, right? So in both the cases we pushed the dollar symbol, and then at the end we removed the dollar symbol. But at the beginning we said that when we defined the PDA, we said that the stack need not be empty, right? So this is what we said. We said that the stack need not be empty, right? So what I am saying is that given a PDA, suppose it accepts, so it need not check the status of the stack while accepting, right? It need not check the status of the stack. So the claim is that if there is a PDA which does not ensure that the stack gets emptied while accepting, because that's not something that needs to be ensured, we can modify that PDA into a PDA which always empties the stack before accepting, right? So suppose there is a PDA 1 that, or PDA P, that need not necessarily empty the stack. We can transform it into a PDA P dash which always empties the stack. So how do we do that? So basically we artificially ensure that the stack gets emptied. So we need to do two things. We first insert a special symbol into the stack first, right? So let's say the dollar. So this special symbol is not something that is that is used by the PDA already. Okay, so the PDA already uses a dollar, you find another symbol which is not used by the PDA. Basically this has to be unique. So before the PDA starts operating, we push the dollar into the stack. So that's what I show here. Suppose this was the old start state. Now we modify it into by adding a new by pushing the dollar symbol and adding an extra state. So whatever transitions the old, let's say it had, let's say it went to, there are two transitions. Those two transitions will happen from the new state here, right? So it is exactly the old PDA, but we are pushing a new symbol into the stack at first, right? Okay. Now, so now we have this dollar at the bottom of the stack, which is a unique symbol, which is not used by the PDA. Okay, and the thing that we need to address is, suppose the PDA accepted without the stack being empty. Now we will force it to empty the stack. So how will we do that? So suppose this was the old accepting state, right? So now this accepting state, we do this. So we modify it like this. So this state becomes the first state out of the three that I have drawn here. We replace it by a series of three states. So first let's say this is state, let's say Q10 or something, or Q10. Then what, this is Q10 and this is some two new states. Okay, this is new and this is also new. What we do is, first we have from the Q10 we make an epsilon transition to a new state, right? So that there is nothing read from the input and no movement to the stack. And from the new state we are able to move to another new state. So maybe I'll call it new 1 and new 2, right? From new 1 you are able to new 2, and new 2 is the accepting state. And what we do is, before going to new 2, we ensure that the stack gets emptied. So there is a loop on new 1 where we are able to empty the entire contents of the stack, right? The loop on new 1, we are able to empty the entire contents of the stack, whatever was the original stack alphabet, and the only way to move to new 2 is by popping out the dollar that we had originally inserted at the beginning. So for every accepting state like Q10, we add these two new states, right? So this could be two new states added to every accepting state. So this ensures that whenever it accepts, the stack is empty. So even though it is not a requirement that the stack is emptied while accepting, given a PDA, we can convert it into a PDA which always empties the stack, right? And finally, one more modification or one more thing that I wanted to say is that, suppose there is a PDA, right? We said that, so if you look at here, there is a push but there is no pop. In this transition there is no push, no pop, right? Here also there is no push, no pop, like I am talking about this one, right? And here there is a pop but there is no push, right? So in any transition it is not required that there is a push or a pop. We could have both of them happening, or only one of them happening, or neither of them happening, right? So the third point is that as per the rules of a PDA, we are allowed to have 4 types of transitions. One where there is only push, one where there is only pop, or one there is both, and one there is neither, right? So the claim is that we can always convert the PDA into an equivalent PDA, right, where every transition has one push or one pop but not both. So meaning the every transition will be of the types 1 or 2, right? So if it is type 1, we can retain the transition. If it is type 2 also, we can retain the transition. If it is type 3, if a transition has both push and pop, right? So what I mean is, if it has both push and pop, something like some symbol X, now A goes to B, right? Now what we can do is we can split this into 2 steps by introducing a new state in between. First popping B, sorry, first first popping A and then pushing B, right? This is what it means, right? First popping A and then pushing B. So when there is both push and pop, we can introduce a new state and ensure that the push and pop are separated. When there is neither push nor pop, right? So when there is a transition that does neither, right? It may just read the input or not even that. Then we artificially push something and pop the same thing, right? So when there is neither push nor pop, right? So something like this, X. Then again we introduce a new state in between and we push some dummy symbol into the stack and then you pop it. So that there in the two transitions that replace this one transition, there is one push and one pop. So it's kind of a workaround, but as a result we can have a PDA where every transition includes a push or a pop, but not both, right? So these are the three equivalent forms, meaning given a PDA that does not satisfy this, we can convert into this without any loss of generality, right? So whatever, if you have a PDA that does not have a single accepting state, we can convert into a PDA, convert into one that has a single accepting state, right? Without changing the language. If there is a PDA where the stack is not emptied, we can convert it into a PDA where the stack is emptied, again without changing the language. And if there is a PDA which sometimes does both push and pop in a transition or does neither of them in a transition, we can convert into a PDA where every move has a push into the stack or pop out of the stack, but not both, right? So these are the 3 points that I wanted to mention first. The next thing I wanted to mention is we saw that context-free languages are not closed under intersection, right? We saw an example. However, we know that regular languages are closed under intersection. So natural one question is, what if we take a regular language and a context-free language, let's say A is a regular language and B is a context-free language, and consider the intersection of A and B. So the claim is that A intersection B is going to be a context-free language. So we know regular intersection regular is regular. Context-free intersection context-free need not be context-free. We know examples where it is not context-free. But here I am saying that regular intersection context-free is necessarily context-free. So we will not do the full proof, rather we will just give a sketch of the proof, because we have seen the ideas of this proof earlier. So suppose A is a regular language and B is a context-free language, right? So which means there is a DFA M that recognizes the language A and there is a PDA P that recognizes the language B. So if you recall, while we showed that regular languages are closed under union, right? So we built a certain DFA using, so basically if we had 2 DFAs, this was our first proof before we discovered NFAs, where if you had 2 DFAs, we built a DFA where the states of the new DFA were Cartesian products or Cartesian pairs of the original DFA. So if this was DFA 1 and this was DFA 2, right? Sorry. And this was DFA 2. So basically the movement in the DFA 1 is mimicked by the movement, the horizontal movement, and the movement in DFA 2 is mimicked by the vertical movement, and this is combined in the DFA whose states are the Cartesian products of the original DFAs, right? This is what we did to show that regular languages are closed under union. This was the first proof before we discussed NFAs. So the same idea works here as well. So we have a DFA M and a PDA P, right? So we make a Cartesian product of these, right? So we have a, so I'll just replace this. So this is DFA M and this is let's say PDA P, and the states are Cartesian pairs. So the movement on the DFA is mimicked by the horizontal movement, right? and the movement on the PDA is mimicked by the vertical movement. So if it is both moving horizontally one step and vertically one step, you do this, right? You move diagonally. Okay. In this figure, it's just as an example, I've just drawn 2 and 3, but it could be like if the DFA has 10 states, PDA has 20 states, it would be a 10 cross 20 grid, right? But the PDA, in this case, there are a couple of things that are different. The PDA has a stack, while DFA does not have a stack, which is okay. So I can have maintain a, so this resulting structure, right? This resulting structure automaton, which is a combination of DFA and PDA, will be a PDA, because PDA P has a stack, and now that stack can be retained because M does not have a stack. So the stack operations can be done as per PDA P, and just the state operations we follow the Cartesian thing, right? So just going through the details. The DFA M has states Q1 and transition delta 1 small q1 F1. So states Q1 and accepting states F1. PDA P has states Q2 and accepting states F2, right? And the new PDA that is constructed, the states will be cross product Q1 cross Q2, and the stack of the new PDA will be kind of, it will be faithfully reflecting the stack of P, because that is possible. We don't, because M does not have a stack. And the transition functions are, we use the same idea as before. It combines the moments of the transitions in M and P. And the accepting states will be, so in the case of union, we had this thing that either we said that for the union of languages, we said that either the resulting states, let's say x, y, or x1, x2 should be such that either x1 is an accepting state of the first machine, or x2 is an accepting state of the first machine, or, right? Or the key thing is that we had an OR operation. However, here we are talking about intersection. So we want both M and the PDA to accept. So both x1 should be an accepting state of the DFA M, and x2 should be an accepting state of the PDA P. In other words, this means that the set of accepting states of the new PDA should be just basically F1 cross F2. Basically, it's a ordered pair where the first element comes from the accepting state of M, and the second element comes from an accepting state of P. And if you recall, we even mentioned this briefly while discussing the proof of a union. Regular languages are closed under union. We said that by changing the accept states into F1 cross F2, we get the closure under intersection. So this is the same thing. The accepting states is F1 cross F2, states is Q1 cross Q2, and the stack, because only one of them has a stack, that faithfully reproduces the stack contents, right? There is also, that is pretty much the idea, but otherwise the details of the proof are pretty much same. So my suggestions is to work out the details of this proof, just to give yourself a idea of how this proof goes about. And that's pretty much what I wanted to say in this lecture. So we saw these 3 modifications of the PDA. We can do these modifications, but still it will be equivalent to the original PDA. We can modify, we can convert it into a single accepting state. We can convert into a PDA where it empties stack upon accepting. We can convert into a PDA where every transition includes a push or a pop, but not both. And then we said that if A is regular, B is context free, then A intersection B is necessarily context free, and we gave the sketch of the proof. And I suggest you to work out the details of the proof. And that completes lecture 21, also completes the lectures of week 4. So in this week, we We first saw Chomsky normal form, which is a specialized form for representing context-free grammars. Then we saw a CYK algorithm, which is an efficient algorithm to check whether a given string is generated from a given grammar. As long we can do that, we can apply this algorithm as long as the given grammar is in Chomsky normal form. Right. We then saw closure properties of context-free languages, including this one, which is also kind of a closure property, right? Intersection of regular intersection context-free is context-free. And then we saw PDAs, we saw definitions, right? And we saw some examples. And that completes week 4. In week 5, we will continue discussion on context-free languages. So, in fact, we will see that the class of languages recognized by PDAs are also the same class as context-free languages. So, there is an equivalence here, much like regular languages are those that are recognized by DFAs as well as regular expressions. So, here also context-free languages are those that are recognized by context-free grammars as well as PDAs, right? So, there is an equivalence. One is a language grammar based model and one is a machine based model. And we will see more like why they are equivalent, why PDAs are equivalent to context-free grammars, and we will see more details about context-free languages in the upcoming week. So, see you in the next week and thank you.